All right, so talking about transformers, point D. So we just said that in a transformer, as AC, or I could say chop DC, is fed into the primary winding, a magnetic field expands and contracts from and around the primary winding. And that magnetic field is going to go through the core, the soft iron core, which then transfers the magnetic field out to the secondary. So if another coil, and that would be the secondary now. If another coil, which we shall call the secondary, is placed within the field of the primary, is placed within the field of the primary, what happens? Coil. A voltage, that's it, a voltage will be induced within the secondary. Within the secondary. If the secondary is placed within a circuit, let me just do this here. So, is the primary within a circuit?
Yes.
It is. How can I tell that?
Because it has the coil going around. It's continuous.
Okay, it's a continuous circuit. So I put my soft iron core. I've got my secondary. Is my secondary within a circuit?
No.
It is not. And this says if the secondary is placed within a circuit, which it's not right there, current will flow. Which is also to say if the secondary is not placed within a circuit, will current flow in the secondary side?
No.
Why not?
Because there's nothing to flow through.
There's none to flow through. All right, F. If the secondary is not connected to a load, if the secondary is not connected to a load, no current will flow in the secondary. No current will flow in the secondary. What about the primary?
Yep.
Well, let me ask you this.
Ask away.
Where do you have a transformer? What was the last transformer you probably used?
My house.
Magnetos.
Your whole house?
Yep.
You didn't use a magneto today.
Phone charger.
Your what?
Phone charger.
Phone charger.
Phone charger, yeah.
So your phone charger. Well, did your phone take 60 hertz 110 to charge?
No.
So you have a transformer. That's what that little thing is.
Step down.
Yeah, step down. So it's a little transformer. And if you leave it plugged into the wall, how much power does it use?
Zero.
Depends on what it says.
Depends on what it says. All right.
Wait, what?
So in addition,
Find the
if secondary is not connected to a load, is not connected, not connected to a load, the primary will consume very little power. How do you know this to be true?
It's resistant of this.
I have
Oil.
What's that?
You plug your phone in, it takes charge.
You have bills to pay. All right, so I go home and I grab my, well, I have an Android, so everything's different. You guys get your Apples. You have your little white little
Here, you want my cat?
Cube.
I got
To the wall.
It's all right. Everybody knows what that is. It's got your little cube. Well, let me see a cube. No, don't throw it at me. Jesus.
Jesus.
Put an eye out. Okay. So I'm going to plug this into the wall. And how hot is it going to get?
It's gonna stay pretty cool, Kevin.
It's going to stay pretty. Why is it staying cool?
There's no love
The
now.
secondary winding doesn't have a load.
That's right. And now I'm going to take Tim's, and I know Tim happens to watch a whole lot of YouTube. I plug in Tim's iPad. How hot is this little cube going to get?
Really hot because it needs a lot of power.
Okay, so why is one getting hot and one not? Because the only one is actually doing anything. So that one has to plug it in. Now it's got stuff going through it. This is not doesn't really have anything going through it. So it stays cool.
But why, Kevin?
You really don't put things?
Oh, just messing with you. That was funny. I'll throw it back at you. All right. So if you don't have it connected to load, it doesn't get hot because you don't have power flowing through it, and that's a good thing. It kind of saves you money. Doesn't say none. It says very little. All right. Counter. This is why. Counter. Oops, that's an N. C-O-U-N-T-E. Counter EMF. We talked about that already, right? Lenz's law and all that good stuff. So as the field builds up in the primary, what does it want to do? Now, field builds up in the primary. What does it do to the current coming in?
Opposite to the current.
It opposes the current coming in. So it builds its own resistance. What is that resistance represented as?
XL.
Oh, look at this guy over here, X of L. Remember that?
No, that was last week, Kevin.
I know. It's not really resistance, but it acts like resistance. So the X of L, so we have X of L, so we have this inductive reactance, kind of the same thing. So counter EMF is going to build up. It's different, but it's the same theory. Counter EMF is going to build up, so prevents current from flowing in the primary. So what's happening is the EMF is building up to such a high degree in this little transformer coil that it actually shuts down any current from flowing in the primary.
So it like basically self-regulates.
It's self-regulating, self-shuts down. So counter EMF prevents current from flowing in the primary. Is that all I wanted to say? When there is no load. When there is no load on the secondary. I think this is kind of cool. So when the secondary is connected to a load, we'll come back up here. Maybe we'll connect it to a load. Let's make it a resistor. When the secondary is connected to a load, the magnetic field in the secondary, so remember what happens. We have a buildup of a magnetic field across the windings. So what is induced in the secondary? Voltage is induced in the secondary. That's correct. I have voltage that was induced in a coil. What does that create?
Current
Current and
EMF.
and a magnetic field.
Magnetic.
So this secondary has a magnetic field. What's a magnetic field going to do? It's going to expand.
Back.
Expands back that way. It's 180 degrees out of phase, or it opposes the original EMF coming out, the blue, and so it then unloads it and allows current to flow. So it gets rid of the counter EMF. Pretty cool, I think. So when the secondary is connected to the load, did you follow that? When the secondary is connected to a load, the magnetic field, the magnetic field in the secondary counters. It kind of counters the counter EMF. CEMF. Counters the counter EMF in the primary and allows current to flow in the primary. Now, I wrote this. I don't know if you like it. I found this in a book. I thought, oh, it's kind of cool. Maybe not. I don't know. It said, consider the field as a power reservoir. If the secondary draws current from the reservoir, the current must flow in the primary to fill the reservoir. I don't really like it. Therefore, the current flow in the primary is directly proportional to the current flow in the secondary. I'm going to go with that one, though. The current flow in the primary is proportional. I'll say directly proportional to the current flow in the secondary. Notice I didn't say the same. I said it's proportional. It's not the same. Could be, but probably not.
Why isn't it the same, Kevin?
I don't know. Nobody really knows for sure. It's an unknowable fact. No, I'll tell you in a minute.
I know, that's what I was.
I know. All right, transformers. Are used to do what? I've already said this once.
Step up and step down voltage.
Okay, step up, step down voltage. Step up. Can't keep my place tonight. Transfer step up or step down voltage. Step up or step down voltage. What's an example of a step-down transformer?
Phone charger.
All right, there we go, phone charger. Step-down voltage or current. Kind of works both ways. The ratio, I hate that word, the ratio of EMF in the primary to the EMF in the secondary, ratio to the EMF in the primary to the EMF in the secondary is equal to the ratio of the number of turns in the primary to the number of turns of the secondary. Which is to say, this entire ratio of what happens between the voltage in the primary to the voltage in the secondary, and also the current in the primary and the current in the secondary, is going to be completely dependent upon how many turns of wire there is between one to the other. So you could literally count them, and you would figure that out. So, let's see, B example. Example, if the primary has 100 turns and the secondary has 200 turns, the EMF, what's EMF? Another word for EMF. Mama, be proud, say it.
Dielectric current.
Dielectric current.
Frequency.
Oh my gosh.
Don't say a lot.
It's another word for EMF.
At least he tried.
What?
Electric.
Really?
You gotta go back to week 2.
All right, we're starting all over again.
Great. Magnetic field.
Voltage.
Just throwing shit out.
I noticed. At least the right thing out there. It's voltage. Secondary is 200 turns the EMF, or I should just write voltage in, I guess, if it's going to be a problem, in the secondary. And the secondary will be how much more?
Double.
No, twice. Twice as much as in the primary. So how about a formula? Some of you guys need some formula, I think. All right. EP over ES is equal to NP over NS. Care to guess what that is? E of P is?
Voltage of primary.
Voltage in the oh, okay. Waking up. Voltage of primary. E of S then is voltage
Secondary.
of secondary. And P is,
Number of windings in the primary.
okay, there we go, number of turns. And wow, I don't know what the heck I'm spelling there.
Norm.
The numbers.
The numbers.
Number of turns of the primary. And N sub S is number of turns secondary. So if we kind of look at that and we said, well, we could make up an example. So E over P, EP over ES is equal to NP NS. What was my example over there? Had 100 turns in the primary and 200 in the secondary. Well, what if I had, why not, 50, I had 50 volts in the primary. How many volts do I have in the secondary?
100.
Well, we can do it one way, just look at it and go 100 is 200 is 50 is to 100, so it becomes 100. We could solve it. Solve it long way. 500 times 200 is
10,000? 1 million?
is it 10,000? What did I get? What was I saying? 50, 1, 2, 3, 5 is 10 plus 3 zeros, so 10 plus 3 zeros. So it is 10,000. So 100x equals 10,000. Divide both sides by 100. And x equals, what's my voltage of the, cancel each other out, subtract 3 zeros.
100.
X equals 100 volts.
Whew, that was hard.
Yeah. Is it really that bad today?
It's a Monday, Kevin. You just hang in there.
Or we
We'll
could,
get through it.
or I guess we could go like this. Well, 100 goes into 100 one time, goes into 200 twice. 50 times 2 is 100. X is 1, so do it that way too. So 50 times 2 is 100 equals 1x. So whatever you want to do it. Don't want to make it complicated here. All right, so that's how you can do something like that. Yeah, I got to maybe quit drinking or something. Time to sober up before we get here. All right.
It's break time. That gets you.
We could just skip break time. Thank you.
Gee, thanks.
So you're saying
Keep in mind. You got something you got to keep in mind here. I should just put everything I've already said. Keep in mind that a transformer cannot create power. So, if the voltage goes up, I'm afraid to ask, what was the formula for power?
Pi.
So power equals
Voltage.
I times E. If the voltage goes up, what, and you can't create power, what does the current have to do? It's got to go down because P is going to stay the same. It would be great if you could build a transformer, you could plug into the wall, power and current both go up, wouldn't it? It wouldn't be great if you're selling power. So, so voltage goes up, current must come down.
Wait, so if the voltage goes up?
Current has to go down. You can't create power.
You just forgot voltage, that's all.
Huh?
If it goes up.
Keep in mind that oops,
So it goes up.
if that a transformer cannot create power. So if the
Yes.
thank you.
If it goes up.
Sorry.
Yeah, Kevin, we should lay off the alcohol, kind of sober up before we come in.
That does not apply to me. So if
The voltage.
remember, joke around. I don't have to write anything. Keep it up.
Somebody get this man alcohol.
My hand soap is right in my office. Just the soap teeny. Keep that a transformer cannot create power. So if the what do you want me to write here? Voltage.
Goes up.
That makes sense.
So if the voltage goes up, current must come down. Current must come down to compensate. I'm not going to compensate. So,
Like that on the test.
right. In a transformer, that is 100% efficient, which is not. Most are 90 to 98, which isn't bad. Amperage in the primary is inversely proportional to the amperage in the secondary. Amperage in the primary is inversely proportional to the amperage in the secondary. So that is E of P. What is that again? Voltage in the primary versus ES. All right, before I write this, we were talking about inversely proportional. Do you remember where else we ran into an inverse proportional problem?
Capacitor reactance.
Gear ratios. So what'd you have to do? Flip it. So this is going to be the secondary, and this is going to be the primary. So that's I of S, I of P. Or we could put it all together and say turns of the primary over turns of the secondary is equal to voltage in the primary over the voltage in the secondary, which is equal to the current in the secondary over current in the primary. Six. If the primary has fewer windings, is that possible? Primary has fewer windings, mostly fewer windings than the secondary. It is a step-up transformer. If the primary winding has more than the secondary, it is a,
Step down.
there we go. If the primary has more windings than the secondary, it is a step down transformer. So a step down transformer will do what with the voltage? Step down
Lower voltage, raise amps.
transformer. Ooh, I like that transformer. Will increase or decrease voltage? You sure? All right, we'll decrease. We'll decrease voltage, but what to the amperage? Okay, increase. Formulas are the same. They don't change. So formula is the formula. All right, so we can skip that. I'll just say so. Power. Well, no, that's actually a good point. So, good way to sum it up. Remember. Remember that power, which is volts times amps, in power in must equal power out, assuming it's 100% efficient. Assuming it's so, as voltage goes up, current comes down. If voltage goes up, so voltage goes up. If voltage goes down, what happens? Current what? Comes or goes up. You guys are a dead crowd. But still, don't forget to tip your waiter.
You get paid to be here.
I'm not your waiter. All right. Your server, I'm sorry. Primary has 150 turns, and secondary has 300.
Just step up.
Input is 120 volts AC. You suppose that's peak to peak or peak?
Peak.
Thank you. What is input and output? What? I move it over? No? A little bit? Not a little bit? Pause. Let's bring this back up and let's see if we can solve this thing. Let's see if you've solved it. So what's the formula I want to use?
EP over EX.
So I've got 150 turns to 300 turns, was that it? And 120 volts AC input. So, all right, so here's my input. Basically, here's my primary is over on this side, so my primary. So it is, what, turns primary over turns secondary equals voltage of the primary over voltage of the secondary equals the current of the secondary over the current of the primary. All right, so 150 over 300 equals 120 over X. So what do you got? 150 goes into 150 once, goes into 200, 300 twice. So cross multiply of 1x equals 240. So that'd be 240 volts AC. What about current? Can I solve for current?
We need resistance.
I didn't give you any resistance or anything, so nope, can't solve for that. But anyway, that's pretty much it right there.
Wow, we done did it.
Let me see. Actually, let me think. Can we do the current?
Yeah, we can make a
Oh,
curve.
we could have if I would have gave you the rest of the problem. What if the output has a 100 ohm load? Now you should be able to figure it out. Tim, you done? That's you in the front row. You done? Got it? What's the answer? He's silent. Did I break you? I know this is going to come as a horrific shock to you.
2.4 amps on the secondary, 1.2 on the
But there's this thing called EI and R. EI and R. And we determined that E of the primary so far is,
120,
we didn't even determine it was given to you. So the E over here is
240.
240, and the resistance over here is 100 ohms. Therefore, the I is
2.4
2.4
amps.
amps. All right. Now, how am I going to come back over here and figure it out? Well, there's a couple ways. One, you can figure what is the power over here. What is my power? 76?
576.
576 watts. Did this transformer magically create power? So what does my power over here have to be?
Less than 5 cents.
Well, it's actually going to be less than 576, but since I didn't give you anything else, I'll assume it's 100%. Therefore, I can just fill in for I, or I can use the formula over here. Vs Vp equals Is, so voltage in the primary, 120 over 240 equals I of S. I of the secondary is 2.4 over X. I could solve that way. I could figure, since P equals I times E, or I can do the little pyramid, PIE, and I want to solve for I, it is P, 120, divided by 576 equals, so I can use either formula here. You have two ways to do it to get I, and I is therefore 4.8. And if you didn't want to do it that way, you could also figure that this times 2 is that, therefore this times 2 must be that.
It'll
So,
always be times 2 if it's not 100%.
what's that?
So it won't always be a direct times 2 though.
No, it's a ratio.
Yeah.
So what if it was 150 turns on this side and 900 on the other side?
Yeah.
Then what's the ratio? It's a lot more than 2, right?
Yeah.
Okay, so you just figure that out. So you have to do the ratio. That's why it's important to put 150 over 300. It sets up the ratio. If I would have said 150 over 900, then what is that, 6? So it's six times. All right, we good with that? 'Cause that's all I'm gonna say about that.
That's all you're gonna say for tonight?
What about the ohms and those?
Yeah.
What about the ohms on the other side? I don't want to break you guys, but I know this has come as a horrific shock to you. But it's E equals I times R, so R is going to be E divided by I, and I can
Kevin,
get.
we better stop right now.
I know. Whoa, whoa, whoa! Where did that come from?
I think it's got my brain. I think it's got laminated.
All right, we still got lots of time left.
Monday.
Yeah.
You guys are in a hurry to stand in front of that time clock, aren't you? All right, fine, and that's all I got to say about that.
Oh, come on. Hey, pipe down over there.